Okay, so we'll continue our discussion. So what we have been looking at is solving the system of linear. We'll continue our discussion in that line. So what we have done so far. So Ax is equal to b. That's the problem that was given to us. So in general, A can be a matrix of the size m by n, and B is a vector of size Rn. Then the question that we ask is, does there exist an x? Does there exist an x in Rn such that Ax is equal to B? Correct. So that's the question that we ask, and I think we settled the answer to this question, whether there exists an A and whether that X is unique or not, right? So existence and uniqueness was done. Existence and uniqueness was done. Okay. The second thing that we want to ask is how to actually compute this X, right? How to compute this X. So while computation of this X, and the third question we ask is sensitivity analysis, right? So these are the three things that we want to look at, we want to understand for this system of linear equations Ax is equal to B. So this thing was already done. Okay, here we understood LU or Gaussian elimination. Okay, so this we actually studied in the last class. And today we will start with another important decomposition, which is called as QR decomposition. And this decomposition will also help us. Compute the solution to this system of equations Ax is equal to B. So, like in the case of LU decomposition or Gaussian elimination, where we had assumed that assumption was m is equal to n. Okay, it is a square system of linear equations. Here also we start with this assumption. Okay, assumption m is equal to n. Okay, so we start first with square matrix A, and then we'll extend this square matrix A to a rectangular matrix A for QR decomposition as well as SVD when we study. Okay, so the objective now in the next couple of lectures or whatever 3-4 lectures we may require to cover this QR decomposition. So the objective is to understand this QR decomposition, how typically it is done. I'll just give you an overview. You can relate this with classical Gram-Schmidt orthogonalization procedure that you already have studied in your previous linear algebra courses. And once you understand this QR decomposition, we'll see how we can use it to compute the system of linear equations. Okay, so that is what we really want to do. And once we understand this, then we will go to the next topic, sensitivity analysis. Okay, possibly this week or next week, we'll see. So this is the plan now. So the plan is we have covered this much, and now we start with this topic. Okay, QR decomposition. So in QR decomposition, the most important thing that you encounter are the two matrices Q and R. Correct. So this Q and R two matrices are there. Out of this Q matrix is a orthogonal matrix. Okay. So first we want to look at what are orthogonal matrices. Okay, so just quick recall. We had defined something which is called as inner product or dot product, right? I hope you remember inner product, dot product of vectors. So how did we define that? So for vectors x, y belonging to Rn, x transpose y is inner product of x, y is basically summation xi, yi, I going from 1 to n, where x is this vector x1 up to xn and y is this vector y1 up to y. Correct. So this is what we define as inner product. And this inner product actually gives us a very interesting concept that is of angle between the vectors. Okay, so the angle between the vectors is something that is very important. So you can very easily show that this inner product for real vectors, of course we are talking of, so you can write down this inner product as x transpose y, which is same as y transpose x also. It doesn't matter, it is the same. And you can show that this is a bilinear function in the vectors x and y. Okay, so you can show that this is a bilinear function in the vectors x and y. Okay, so this is something that is very important. And basically, based on this inner product, we can define something which is called as norm of a vector, right? So this is also something that you already have seen. So norm of vector x, so I will denote it by 2. The reason will become clear. So is basically the square root of inner product of x with itself, which is basically square root of x transpose x, which is basically nothing but square root of x1 square plus x2 square plus xn square. Okay, so that is what it is. So square root of summation xi square I from 1 to n, and then this 2 comes here. So that's why this square root comes. So it's a 2 norm. If you take pth power and take pth root, sum of p powers in pth root, you get a p norm. Okay. So this 2 norm of vectors basically gives you the concept of distance of the vector from the origin, right? So suppose this is the point x in Rn, then this distance, correct? So this distance is basically 2 norm, right? The way you measure it, right? So the measuring is done by your usual distance formula. Okay, so this comes from so this norm gives rise to the distance between the vectors x minus y, which is equal to summation xi minus yi square I from 1 to n, right? And this is the usual distance formula that we have studied in our geometry, right? Usual distance formula we studied in coordinate geometry. And we can define the angle between the two vectors also. And the way we define angle between the two vectors is using this formula. Cos theta is x transpose y divided by 2 norm of x, 2 norm of y. So here theta is actually the angle. So it's an acute angle between the two vectors. It's the angle between the vectors x and y. Okay, and x and y are orthogonal, that means they are perpendicular if and only if x transpose y is equal to 0. So if x transpose y is equal to 0, then you have cos 0 is equal to 1, so theta is equal to pi by 2. So this is the concept of angle between the two vectors. And something that needs to be understood is that how do you really visualize this angle between the vectors? Like if you have vectors in 2 dimensions, like the figure I have drawn. If you see the figure I have drawn here, then in that plane, you know how to define angle between the two vectors. But in R3, R4, R100, say for example, what do you mean by angle between the two vectors? Basically, what you are looking at is you are looking at the plane which is spanned by these two vectors. Okay, so if the vectors are not on the same line, then they will span a plane in R whatever space, Rn. And in that plane, you can visualize the two vectors are lying on that plane and the angle between those two vectors. That's what it really means. Okay, so that's how you visualize. So angle between the vectors, basically this is what is there. So these vectors are orthogonal, and then what is an orthogonal matrix? Okay, so orthogonal matrix. So orthogonal matrix is a matrix whose columns are orthonormal. Okay, so there is one more added condition. Orthonormal meaning that they are orthogonal and each of them are with unit norm. Okay, so a matrix. So a matrix Q in Rn cross n is called as orthogonal matrix if you can write down q transpose is equal to identity, which really means that q transpose is the inverse of q, correct? So calculation of inverse of this matrix, orthogonal matrix, is really very easy. You just have to take the transpose of the matrix and you get q transpose. Something interesting that you have to notice here is that in the previous case also, when you were doing LU decomposition and you wanted to take inverse of L you did not compute. You just read the entries of inverse of L from the entries of L, right? So these type of algorithms are really very important because the computation of inverse is not actually a difficult task in this particular problem. Okay, so that's why these type of algorithms, this type of examples are really very important. There is another importance of orthogonal matrix over LU decomposition. So that I will try my best to explain, but let us see how best we can. Okay, so suppose this matrix Q is such that columns are Q1, Q2 up to Qn. Okay, it's an Rn by n. Then Q transpose is equal to identity, which is equal to Q transpose Q, implies that columns of Q, which are nothing but Q1 up to Qn, is an orthonormal set, correct? Orthonormal set. And what does this orthonormal set means? Qi, Qj inner product is equal to delta Ij for Ij equal to 1 to up to n, right? So when I is not equal to j, it's 0. That means the orthogonality. When I is equal to j, then you have inner product equal to 1. Inner product equal to 1. Qi inner product equal to 1 basically means that you have norm of that matrix to be equal to 1. Okay, so why these orthogonal matrices are really very important? uh, yes, anything you want to say? Okay, so why these orthogonal matrices are important? So one of the important properties of orthogonal matrices, okay, is the following. Properties of orthogonal matrices is the following. Okay, so if Q is a orthogonal matrix, n by n, if Q is an orthogonal matrix, then for any xy vectors belonging to Rn, what do we have? We have two properties satisfied. Inner product between Qx, Qy is same as inner product between x and y, and norm of Qx is actually equal to norm of x. So these two properties are really very important. How do we prove them? Proof is not really very difficult. So you start with inner product of Qx, Qy. By definition, what is this? Qx transpose Qy, which is nothing but x transpose q transpose qy, correct? So I can use matrix multiplication is associative. I get x transpose y, which is nothing but xy. And similarly, I can prove the other result also. X is equal to y. If I put, then I will get qx is equal to norm x square, and I take square root. Okay, so this is not a difficult thing to prove. But what is the consequence here is really very important. Okay, so what is this? What is this property really saying? Okay, so this property, if you want to understand, then think of a matrix. Think of a matrix as a linear transformation. Linear transformation from Rn to Rn. So in particular, you take n is equal to 2. If you take n is equal to 2, then this is R2, and I have a linear transformation, suppose by a matrix A. So it is mapping R2 to R2, correct? So this is the transformation that I have. And what happens, because it's a linear transformation, it's enough for me to see how it affects the basis, then the entire linear transformation is understood. But if you see several linear transformations, so in particular, if I take A is equal to 10 9 9 8, okay, suppose I take 10 9 9 8, can you tell me what is the action of this matrix on certain vectors? Okay, so for example, what will happen to 1 1? So where is the vector 1 1 here? So the vector 1 1 is here. When you apply this matrix on vector 1 1, what does that mean? This is the action. What do you get? What do you get?
19, 17.
19 and 17, right? So you get 19 and 17. So this particular vector here, 1 1 in the domain, where does it get mapped to? It get maps to 19 17. So it goes like this, right? Really very far. So this is the transformation A makes onto this vector 1 1. Now what happens to the vector 1 minus 1 or minus 1 1? What happens to the vector minus 1 1? So minus 1, 1 is this vector, right? The pink vector. What happens to it? So if you have minus 1, 1, then you have to have
Minus one,
yes,
minus one.
minus 1, minus 1. So minus 1, 1 vector here. So this is minus 1, 1 vector. Where does it go? It goes to minus 1, minus 1. So minus 1 is somewhere here. Okay, so uh, so this is minus 1, 1. So this vector is minus 1, minus 1 roughly. Though these two vectors are looking like they are on the same line, they are actually not. So my drawing is really not good. Okay, so this is 1917. This is the vector. So now you see what is this linear transformation A doing? Are you convinced that this linear transformation A is changing the length of this vector? See, length is square root of 2 here. That length goes to what? Square root of 19 square plus 17 square. That means that you really have a huge magnification of this vector 1, 1. Whereas for some other vectors, minus 1, 1, the length is still square root of 2. The length does not change. It is still square root of 2. Okay, so for some vectors, the length is changing. For some other vectors, length is not changing. For some other vectors, the length will actually reduce. The length will actually reduce, correct? So all these different things will happen, for example. Now the second thing that I want you to observe is that what is the angle between these vectors minus 1, 1 and minus 1. So what is the angle between these two vectors? So this is 90 degree. So this angle is orthogonal. These vectors are orthogonal to each other. Yes. But what happens here? Here you see the angle between their images. The angle between their images is almost 180 degrees. It is not exactly 180 degrees. These vectors are not on the same line, but it's almost 180 degrees. You understand what is really happening here? So this linear transformation A is actually sending orthogonal vectors almost on a straight line. At the same time, what is this linear transformation? What is this matrix A doing? It is sending this vector 1, 1 to this vector 19, 17. That means that it is changing the length of the vector also. So this is something that you probably may not want to see. Okay, why? We will see little later. But this is something that is not a good idea. Orthogonal vectors, you are almost sending them to the straight line. What does that mean? The best possible linear independence is destroyed, right? So the best possible linear independence is here. It's destroyed and you are making them almost linear in the image space, right? This linear transformation A is behaving in that fashion. Now you see this in context of the orthogonal matrices. Okay, now you see this in context of orthogonal matrices. What is happening with orthogonal matrices? You are saying that the angle between the images qx and qy will be same as angle between the x and y, because inner product is same. If the inner product is same, then the angle between the vectors will also be the same. Not only that, you are saying that the length of the image will be same as length of the original vector. So the linear transformation q is really very well behaved with respect to the vectors. Do you see the difference? In general, a matrix say that I constructed here does not have this very nice property, that the matrix say will not preserve the angles between the vectors in the domain. At the same time, it will not preserve the norm of the vectors in the domain, but orthogonal matrices will do that. And that is something that is really very interesting and very important. Okay, so this particular example 10, 9, 9, 8, and what happens to this 1, 1 and minus 1, 1, and how you get almost a straight line. This is something that is really very important. And this particular example, or maybe little bit more dramatic example than this, generalization of this example, I will take when we discuss sensitivity analysis also. But right now, is the point clear? Geometrically, what is really orthogonal matrices doing? And now with this context of matrix as an operator or matrix as a linear transformation, you can appreciate why people give importance to orthogonal transformations or orthogonal matrices, because they really respect two important things about vectors in the domain in the image space also. The angle between the vectors in the domain is preserved, as well as the length of the vectors in the domain is preserved, right? So that is something that is extremely important, right? So this matrix, you see, it is doing something very weird here. So in particular, what will happen? Orthogonal vectors here in the domain will go to orthogonal vectors in codomain also. Okay, because the angle between the vectors is going to get preserved. So is this part clear? Geometrically, what these orthogonal matrices are doing and why they are important?
Yes,
Is
sir.
it the
Yes, sir.
rotation matrix or
Oh,
are rotation matrices a subset of orthogonal matrices?
sorry, Aviraj, can you say it again?
Are all rotation matrices do they form the whole set of orthogonal matrices, or are
No.
they a set of orthogonal?
No, so we are going to go to rotation matrices and we'll see what is going to really happen. Okay, so rotation matrices will only be part of orthogonal. There are more orthogonal matrices than rotation matrices. Okay, but now that you have brought this rotation matrix thing, so let us just understand the rotation matrix. Okay, anyway, we are going to do that. So one example of the matrix that I give is this example, right? For example, A, which is equal to 0, -1, 1, 0. Okay, so what is this matrix doing? Can you geometrically tell what is this matrix doing? What is happening to xy? So any arbitrary vector xy, when you apply this, what happens? So so x1, x2, correct? 0, -1, 1, 0, x1, x2. So what happens to these vector x1, x2? What is the multiplication?
Sir, it is
x2 minus
flipping
x2.
around y-axis.
Correct. So what is happening here? Any vector x1, x2, any vector x1, x2. Now what is happening to x1, x2? Where is it going to? Can you tell? So what distance is x2? So this distance is x2. This distance is x1. Correct. So if these are the distances, where does minus x1 go? So this is minus x1 and this is x2. So x2 is your first component and minus x1 is the second component. So what is the angle between the vectors? You can also
90
see what
degrees.
is that. 90 degrees. And how, which direction they are being rotated?
Clockwise.
Clockwise, correct. So in clockwise direction, 90 degree, they are rotated and you get this particular matrix, right? So in this particular case, you see, you take any two vectors, their norm is preserved, right? Clearly, x1, x2 is getting mapped to x2 minus x1. The norm of x1, x2 is same as norm of this matrix, right? So this is preserved. And if you check two vectors, you look at the angle between the two vectors, that angle will also be preserved, okay? Why the angle will be preserved? The angle will be preserved because you understand the geometry. So each vector is being rotated by a certain angle. So after rotation also, the vectors will preserve the same angle, right? So that's the reason through geometry. Okay, so this is something that is really very important. This is a very beautiful property of orthogonal matrices, and this property is why orthogonal matrices are really popular in use, and this is why people do not really want to use matrices which are not orthogonal. Okay, so this is important. Another reason about orthogonal matrices used over all other matrices is that um, I'll just state this: multiplication of a vector by an orthogonal matrix is backward stable. Okay, that is another reason. So this is another reason why people are interested in using orthogonal matrices. Okay, because this multiplication does not behave badly. Okay, in other words, you do not encounter subtraction of two nearby numbers or division by 0 when you multiply an orthogonal matrix to a vector, but that may happen in case of normal matrices. So this type of matrix multiplication is much more computationally numerically stable. Okay, so this is something that we will not worry about in this particular course, but this is something that we do it in computational linear algebra course, the other course. Okay, so let us consider these rotators in detail. Okay, so before going to these orthogonal matrices, suppose if I am able to write, okay, suppose if we can write A is equal to QR. What is this QR decomposition? We don't know. But if we are able to write A is equal to QR, what is this Q? Where, so for a matrix A in R n by n, you are able to write Q in R n by n orthogonal and R n by n an upper triangular matrix. Okay. Suppose you are able to write it down, then how does this really help us? Suppose you know how this is done. Then if you want to solve Ax is equal to B, this is same as saying you can do QRx is equal to B. This is same as saying you can do Rx is equal to Q transpose B. Because Q is orthogonal, inverses it's only this thing. And now this Rx, you see, you can solve using backward substitution, correct? So if you are able to construct such a cube, if you are able to construct such a cube that this happens, then you just have to solve a backward stable system, backward substitution, and you will be able to solve the system of linear equations. Okay, so let us go further and see how we can do this. Okay, so consider a 2 by 2 case. Okay, I will first introduce one type of orthogonal matrices. Let us call them rotators. Okay. So first consider the case n is equal to 2. Okay. Plane R2. Okay. And I have this orthogonal matrix Q, which I will write down as Q11, Q12, Q21, and Q22. Okay. So this is what I will do. This is the matrix. And this matrix I want to find. Okay, so Q is such that it rotates every vector in R2 in an anti-clockwise direction by an angle theta. Okay, that's what it is doing. So you have this particular R2 plane. Every arbitrary vector here. So suppose this is the arbitrary vector that you have. Okay, this is the arbitrary vector that you have. It will be rotated in the anti-clockwise direction by an angle theta, and it will go here. Suppose this is the angle theta with which you rotate, then this is what is going to happen. So you want to find out a matrix Q which will actually mimic this operation. Okay, so you want to find out a vector Q which will do this. So how can you find this vector Q? So what are you going to do if you want to find out this linear transformation? What is it that you have to look at? It is just enough. It is just enough to study the action of Q on 1, 0 and 0, 1. Can you tell me why? Why this is true? Can anybody tell?
Because 1, 0 and 0, 1 are form the basis of R2.
Correct. 1, 0 and 0, 1 form the basis of R2. So you just look at the action on the basis. Once you look at the action on the basis, then you are through. Now the next question, why I choose this basis to be 1, 0 and 0, 1 only? Why not any other basis?
Because they're orthonormal unit vectors.
But yeah, that's okay. But why only this? There is another like whole lot of orthonormal unit vectors which are orthonormal basis. Why I choose only 1, 0, 0, 1 out of?
These are simple.
Yeah, why are they simple? You are
Sir,
right.
unit
That's
vectors.
no unit
One and
vectors.
two.
Like I told Kaushiki, there are infinitely many unit vector basis representations, right?
because one
This is
of
not the
them
only.
because one of the terms is zero in that, so that will simplify analysis.
But then that also you have four pairs, no? 1 0 0 1. Then you have 0 1 minus 1 0. Like four pairs you can still build from that also, but you are not taking those pairs. You are taking only 1 0 0 1. Why?
So we can take them as well, but the impact will be same on all the vectors, right? So it does not matter
Yeah.
which two we.
So then why we insist on this? It's very easy. No, Q
Every
is
vector can be easily formed.
Q11, Q21, Q12, Q22, right? When you multiply by 1 0, what do you get? You get the first column of the vector, right? So you get this column Q11, Q21, which is nothing but the first column, right? So when you inspect what is the action of this vector matrix Q on 1 0, that action is going to tell you what is the first column of your matrix transformation. And similarly, when you look at the action on the vector 0 1, it is going to give you the second column of this transformation. So that's why these are spatial amongst all spatial. Okay, so that's why you are looking at the action on the basis 1001, right? So that's how you write the basis. So this is the linear transformation. I hope you know these things. Okay, so that's why I'm looking at it. So wonderful. So if I know this, then again look at the figure. Okay, look at the figure. So suppose this is my 1 0 vector. Okay, this is my 1 0 vector. If I rotate it in an anti-clockwise direction, by angle theta, suppose the new resulting vector goes here. Okay, this is the anti-clockwise direction theta. The resulting vector goes here. What are the coordinates of this new vector? What are the coordinates of this new vector?
Q11, Q2.
Yeah, but what are they? You know the angle is
Cos
theta.
theta, sin theta.
Cos
Correct.
theta.
Cos theta, sin theta. So when you apply this matrix Q on 1 0, what do you get? Cos theta and sin theta. Similarly, this is the vector that I have, which is 0 1, right? So when you apply 0 1, you are going to take anti-clockwise direction rotation of angle theta. So suppose that anti-clockwise direction angle theta takes you here. Okay. So what are the coordinates here now?
Minus sin theta, cos theta.
Minus sin theta and cos theta. Correct. So this is what is really going to happen. So if you see this, then you know the matrix, right? What is the matrix? So Q of 1 0 is basically cos theta sin theta, and Q of 0 1 is basically minus sin theta and cos theta. So if this is what you have, then what is the matrix? What is the rotation matrix that we get? So this implies the rotation matrix that you have is cos theta minus sin theta, and cos theta. Correct. So this is the matrix, and this matrix is such that it will rotate. It will rotate every vector in the R2 plane in an anti-clockwise direction by an angle theta. Is this matrix orthogonal? Is Q orthogonal?
Yes, sir.
Clearly Q is orthogonal. Why Q is orthogonal? Because you know the identity cos square theta plus sin square theta is equal to 1. That means that the norm of the columns is 1, and you can see the columns are orthogonal to each other, right? You take inner product, what do you get? Minus cos theta sin theta plus cos theta sin theta, which is equal to 0. So the columns are orthogonal and the norm is 1. So this particular matrix that you construct is an orthogonal matrix. Wonderful. And geometrically, you can see this property being satisfied, right? So this property, if you see being satisfied, what is the property? It will not change the norm of the vector. That means that it will not scale any vector. Is the vector scaled after rotation? No. If you take two vectors and rotate them simultaneously by an angle of minus theta or theta in the anti-clockwise direction, what will happen? They will preserve their angle between them even after rotation, right? So that's why this property, the property that we wrote down, is also satisfied. Geometrically, we can see here that is really what is happening. Okay. So this is an orthogonal matrix. So now you will say, Okay, why this orthogonal matrix is really very useful. Okay, so why this orthogonal matrix is really very useful is the following. Uh, so one thing that I will be interested in is that uh, the following. Okay, so let us call it as a fact. So what is the fact? The fact is that rotators can be used to create zeros in a vector. So something which can create zeros in a vector is of immediate interest to us. Why? Because you see, what do you want to do? You want this matrix Q, you want this matrix Q in some way be such that it will be creating a zero in A. So if it creates zeros in A, so you look at first column of A. Okay, so this is the first column of A, say for example. Then in this first column of A, you want all the entries zero below the diagonal entry 1, right? You want to produce zeros, you want to introduce zeros in this particular matrix. So any operation which can introduce zeros in a vector, that operation is of interest to us. And here also we can produce the zeros in a vector. Can you tell me how will we be able to produce zeros in any vector X? Can you tell me what you... Huh? Sorry?
x1 cos theta minus x2 sin theta is equals to 0. One first
Correct.
element.
So basically, geometrically, what did you do? You are absolutely right. That's what we have done. The
Rotate the
geometry.
vector such that it falls on an axis.
Correct. So what do? We rotate this vector x1, x2 such that it falls onto the x-axis. So that is the operation geometrically we will really do, right? So let us algebraically write down so that we arrive at the equation that Ramnimas was saying. So let Q be the matrix, which is cos theta minus sin theta and cos theta. Okay. Okay, this is the matrix. This matrix be such that, so I will just do a slight modification in the notation such that Q transpose into X is actually Y0. Okay, so I will choose transpose of this matrix Q transpose X, which is equal to Y0 for some Y. What I am doing is not different than what Ramnivas was saying, right? So I will just rename that Q as Q transpose, but I'll just use Q transpose so that I can write that QR decomposition theorem in a very nice way. So this is what we'll do. So what is Q transpose X then? What is Q transpose X? Q transpose X is Q transpose is cos theta minus sin theta cos theta, correct? So this is your Q transpose. You multiply by x1, x2. What do you get? You get cos theta into x1 plus sin theta into x2 as your first component, and you get minus sine theta into x1 plus cos theta into x2, which is equal to y0. Is that correct? That's what you want. And this is true. When will this be true? If and only if this second component is 0, right? So vector equation is satisfied when you satisfied component wise. So this equation has to be satisfied, right? So this has to be true. So what does that mean? That means that x1 into sine theta is basically equal to x2 into cos theta. So what will you do? So you know the matrix completely, right? How will you know the matrix completely?
We know the and hence we know.
Sorry, what is it? Yeah.
We
Can
can
you tell
calculate
again?
as tan inverse x2 by x1.
Correct. You can calculate tan inverse x2 by x1, and after calculating tan inverse x2 by x1, you know the angle, so you know the matrix. But do you really need to go to that tan inverse x2 by x1 thing? Without even calculating the angle theta, can you come up with what should be sine theta and cos theta? So this equation, if I look carefully, when will it be satisfied? If I say sine theta is equal to x2 and cos theta is equal to x1. Okay, suppose I say this is true, then will this equation be satisfied? The star equation that we wanted to satisfy? Will it be satisfied?
Yes, sir.
Yes, sir.
But are we going to be comfortable with this sin theta cos theta values?
Normalize.
Yeah, you normalize them. Why? Because you want to make sure that cos square theta plus sin square theta is equal to 1. So you normalize them by square root of x1 square plus x2 square, right? So rather than taking these values for sin theta cos theta and have the issue of normalization, what will you do? You take sin theta is equal to x2 divided by square root of x1 square plus x2 square, and cos theta to be equal to what? X1 divided by square root of x1 square plus x2 square. So if you take these values, then without even calculating the angle theta between them, you know what is the matrix? Cos theta, sin theta, cos theta. So you actually have constructed the matrix. And you obtained what you really wanted to do. So you have introduced a 0 here. So you see, this is a very interesting thing, right? This is very interesting thing. You have been able to introduce 0 here. And now what is the other thing that we knew? The other thing that we knew, the property of orthogonal matrices, is that the norm of this vector x1, x2 is same as norm of this vector y0. What is norm of this vector? The norm of this vector is square root of x1 square plus x2 square. So what is the norm of this vector y0? That also has to be equal to square root of x1 square plus x2 square. In that case, when you know this is 0, can you see that this y is actually x1 square plus x2 square? Do you agree that this is what y has to be equal to?
Mod y.
Yes.
There is no other option for y, right? So you can see what really happens by multiplying and calculating, and see, you really do not need to multiply, calculate. Those many computations also you need not invest. If you multiply cos theta, the value of cos theta is x1 divided by root of x1 square plus x2 square. If you substitute that here, and if you substitute value of sin theta here, what would you get? You would get square root of x1 square plus x2 square, right? So that's what you were anyway expecting from the theory, from the result about orthogonal matrices. So you already know what is the result there on the right hand side. You don't even need to compute. Once you calculate what is the matrix sin theta and cos theta, you don't even need to do all of that, right? So you know this matrix, and using this matrix, you can introduce zeros in a vector. Is that okay? Now, where did I use the fact that x2 is not equal to 0? In all of this, where did I use the fact that x2 is not equal to 0? I assumed here that x2 is not equal to 0, right?
X1 can become 0, but if we guarantee that x2 is not equal to 0, then we guarantee that the denominator here is never equal to 0. So the division is always satisfied.
Correct. That's what we are doing. If x2 itself is 0, then we don't want to introduce any more zeros, right? In that vector, you already have a 0 where you wanted to introduce 0 to start with. And if you have a x1 0, yeah, then x2 not equal to 0 guarantees that you are not working with a 0 vector. In a 0 vector, no more zeros can be introduced, right? So you want to take care of that division by x1 square plus x2 square. It should make sense. So that's why you have this particular thing, okay? So now, once you have this particular thing, once you have this particular understanding, what are we looking at? What are we looking at? Given a matrix A in R2 by 2, okay, given a matrix A in R2 by 2. So A is basically equal to A11, A21, A12, A22, correct? So this is what you have as your matrix A. Then what does this calculation, what does this fact telling us? This fact is telling us that there exists a matrix Q transpose. There exists a matrix Q transpose, which is orthogonal, of course. So I will say, rather than matrix Q transpose, there exists a rotator, okay, Q transpose, such that what happens? Q transpose into A, which is nothing but Q transpose of A11, A21, A12, A22. Okay, so what does happen to this matrix? this matrix becomes like this. Correct? So this is an upper triangular matrix R. So what you have really done is that you have found out a matrix Q transpose such that Q transpose into A is actually becoming an upper triangular matrix. Only 2 by 2 case, but no problem, right? You have this particular thing. So Q transpose A is equal to R. This is an upper triangular matrix. So because this is a rotator, so Q transpose A is equal to R implies that A is actually equal to QR, right? So if A is equal to QR, then you achieve QR decomposition. Just a minute. So you have A is equal to QR, right? So you prove this QR decomposition. Well. So A is equal to QR, right? So you prove QR decomposition. So this is the QR decomposition that we prove. This is for 2 by 2 matrices. And what really happens is that Q transpose A is equal to R. So you use this particular construction that you see here. So this construction that you see enables you to construct this matrix. So now, can we do this for an arbitrary n by n matrix? Can we do this? Can we generalize this to an arbitrary n by n matrix? How can we do that? Can you think about it?
So is it like you are rotating the columns of the vector A such that one of the column falls on an axis?
No. So I am not rotating columns of A. I am picking up a column of A, that is the first column, and that column I am rotating. The way I am finding out matrix Q is by rotating one particular column. I am not doing everything together. Okay, so one by one I am doing, and that too entry by entry I am doing. So what will you do? So suppose I have a vector. So now I want to take it to n is equal to 3, for example. So again, I want a rotator. Okay, so whatever that means, rotator in R3, that's what I want. Okay, and what should that rotator do? So I want a vector. So suppose x1, x2, x3 is a vector in R3. What do I want it go to? I want it to go to y00. This is what I want to go. So how will I achieve this? That's the question I'm asking, using the concept that we derived out here. So the hint I want to give is use two rotators. Now geometrically, can you think what we are going to do, and can you tell what will happen?
Rotating across two axes.
Correct. So what will you do first?
We'll first keep either one of the any three of the axes constant
No,
and
so
rotate the vector.
you can say axis x1, axis x2, x3
Okay.
axis. So
Let's first rotate across axis Z. So the
okay.
last entry, the 3 by 3 entry would be 1, and there and other entries would be, and all the entries in column 3 and row 3 would be 0 except the 3 by 3, and other would be the angle by which we want to rotate, and
Correct.
similarly for
So
any other.
basically what you are saying, you're absolutely right. So basically what you are saying, let me try to understand. You are saying that you have XY plane and Z axis is coming out of the XY plane. So something like this, right? So I don't know if you can see the notebook. So this is the XY plane, and this pen, okay, pen probably is not visible. So this, if it is visible. So suppose this finger that I have put on this is the z-axis. Then what you are saying is basically rotate in the xy plane, keeping z as is, like this. So rotate this, right? That's what you are saying. So by this rotation, what you will be able to achieve? You will be able to achieve a zero entry in the second coordinate. Is that what you mean, Harshal?
Yes.
Yes, and once you achieve a zero entry in the second coordinate, then what do? You look at the XZ plane. So that XZ plane is like this and Z axis is like this. You rotate this XZ plane in such a way that you will achieve a zero entry in the third component. That's what you say, right? So that's the idea that you will use. Is that right?
Right.
And in the plane, either XZ plane or XY plane or XZ plane, whichever plane, the way you will introduce the rotator is as follows, right? So the first thing that he is suggesting is that you look at a matrix of this form. What is it? Cos theta minus sine theta. So theta 1, I'll say. Sine theta cos theta. This is the rotator in XY plane and nothing will happen in Z plane. That's what you mean?
Yep.
Correct. So if you apply on x1, x2, x3, what is going to happen? What is going to happen? This x3 is going to remain as is. Correct. And now x1, x2 are only going to change. And the way x1, x2 are going to change, what will you do? You will find out matrix Q. The way we said, we will find the matrix Q, use a similar calculation. And using the similar calculation, introduce a zero, like this zero that we introduced here, introduce a zero. So what will you get? So let us write down, you'll get a y star 0. And I call this matrix Q1, right? So I'll get y star 0, x3. And what is y star? Y star is actually square root of x1 square plus x2 square plus minus. It doesn't matter, right? So that's what this y star is. So this is what I'll get. And now what do? Now I will have this particular matrix. What is the matrix that I will have? I will have cos theta 2, 0, sine theta 2, 1, 0, 0, minus sine theta 2, cos theta 2, correct? So this will be my Q2 transpose, right? So this will be my Q2 transpose. This I'll apply on y star 0, x3. So how will I find out theta 1, theta 2? I will find out theta 1, theta 2 in such a way that I am able to introduce a zero entry here, and then I am able to introduce a zero entry here, right? So this is the zero entry that I introduce. So that rotation I'll find out. So you see here, I had a zero here. Now the way I have constructed Q2 transpose, this zero is not going to get disturbed, right? So this zero goes as a zero here, right? No disturbance to this zero. Only y star and x3 are going to come into the picture, and that y star and x3 is almost like a two-dimensional vector in R2. You construct cos theta 2, sin theta 2, minus sin theta 2, cos theta 2 in such a way that you get a y0. So now it's a two-step operation. So basically, if you combine this two-step operation, then what you really get is that you have x1, x2, x3, this vector. You first construct Q1 transpose to introduce a zero here. Then you construct a Q2 transpose to introduce a zero here. And then you will get a matrix y00 of this type. You will get a vector y00 of this type, right? And now once you understand this, you can take it to any n-dimensional space. So how many rotators you will require to bring all zeros below the diagonal entry 1, 1 of this vector? You will require n minus 1 rotators, right? Then you go to the next vector in the matrix. Then you start introducing zeros below the second diagonal entry and so on and so forth. And you keep on doing this. And inductively, you can show that you will have a train of orthogonal transformations, train of rotators, Q1 transpose, Q2 transpose, Q3 transpose up to Qn minus 1 transpose. Then you will have all the rotators for the second column, third column up to n minus 1th column, right? So n minus 1th column will only require one rotator, and you can write it down very nicely into a QR decomposition. So it's a step by step. It's a step by step thing, and using this step by step thing, you can actually come up with the QR decomposition. Do you understand what is going to really happen? The idea is clear. We'll write this down tomorrow properly in the class, but at least the idea should be clear. So this was the key idea. So how to come up with these matrices Q1 transpose and Q2 transpose, and once you understand how you come up with those, once this key idea is clear, then this is fine. Okay. So I guess the time is up, so we'll stop. But don't log out. There are a couple of announcements I want to make. So the first thing is that